Hello everyone, welcome back. So we are going to continue our discussion about the common base amplifier that you see on your screen. This is a common base amplifier. So in a previous module, we've seen the theory about it and how we can draw the small signal model about it. And from that, we saw how can we derive an expression for the voltage gain, which is the ratio of output divided by input. And then this is your voltage gain. And we've also seen how this circuit can work as a current buffer or provides us the current gain of unity. And therefore, we call it as a current buffer or current amplifier. Then we also understood that it can also be possible to obtain the gain about output voltage divided by input voltage. So that we call it as a trans resistance amplifier. And finally, final part is you can have the output current divided by the input voltage. We call it as a trans-conductance amplifier. So there are four such possibility in almost any configuration using BJT, whether common base, common emitter, or common collector. So all these configurations are possible. So right now on your screen, what you see, I have this BJT in a NPN mode, and it has a collector and the base and the emitter. The base is tied to the ground potential as shown. The collector is the point where I will take my output, and the emitter is a pin where I am going to apply a voltage, input voltage, as shown right here. I call it as a V in. So since the base is common between the input part of the circuit and the output part of the circuit, I am calling it as a CB, common base configuration. So I am connecting this external resistance RC, which acts as a load if there is no external load resistance connected. Then one end of RC is tied to collector pin and another is tied to V plus. That is the supply I'm giving to this circuit. So I have labeled this net as V plus. I have labeled this net as V plus. It means there is a physical connection between these 2 points. In other words, the supply voltage is being applied here, right over here. Okay. And this circuit is complete. Now, if I want to use the BJT or transistor in an active region, I need to provide a DC biasing. And for that, I need to ensure my base emitter junction of a transistor is forward bias and my collector to base junction of the transistor is reverse bias. Okay, so let us understand that. So here is your NP. So there is this PN junction. So P is connected to the ground. So N should be connected to the positive potential so that this junction should be reverse bias. Similarly, here another PN junction. So P is tied to 0 volt, which is ground. Then N should be tied to the negative potential so that this junction will get forward bias. So I know that the cut-in voltage for the input PN junction of the BJT is which is between the base emitter should be greater than or equal to 0.7 volts so that this junction can be forward bias. That's the input junction condition. So what I'll do, I will just right click this voltage source and I will see I gave the bias about let's say 0.7 volts. I click here. So if I have 0.7 volt, let me move this closer. So if I have 0.7 volt at the emitter, base is connected to ground. So this diode at the input side is going to be forward bias. Now with the 0.7 volt here, and the value of ICRC is 1 kilo ohm. Okay, and I need to know the base current, I need to know the emitter current, I need to know the collector current, all these values, so that I will then be able to determine what would be whether my junction at the base collector is reverse bias or not, right? So to do that, the the possibility is that you simulate the circuit to understand its DC operating point. For that, I am using the Spice circuit simulator, and I will run the .op analysis to obtain various voltages and the currents in the circuit. Note that the supply I am using here is 5 volt. So if I use the 5 volt here and I will let the collector current flow through this RC, there will be a drop across this resistor. So with that, I will be able to know that. Now I have used this transistor from the manufacturer part, which is 2N2222. It has a maximum current and voltage rating. We have seen that in earlier modules a lot of times. So if you want to refer to that, you are welcome to do so. Having said this, now we try to get the values. So I will do one thing. I will just click here, run simulation. And with that, I have this notepad or automatic printing pad where I got the values printed for the voltages. So voltage VO is minus 2.7. So you actually see that I have the voltage I expected here to be at the positive, so that my collector is positive with respect to base, but now I have a minus 0.27 volts. So that makes the condition opposite. So instead of reverse biasing, this junction is getting forward biasing. Is that correct? So yes. How about voltage at the mean is minus 0.7. So at the N, I have negative as I predicted, and the P is base is tied to 0. So this PN junction is forward bias. So both junctions are now getting forward bias, making my transistor saturate. And for an amplification, I don't want that. Maybe for using it as a switch, why not? It's possible, but I want linear amplifier, so we'll do that. Now there is a supply voltage 5 volt. Collector current is 5 milliampere. Base current is 26 microampere. So let's say my collector current is 5 milliampere that flows through 1K. So 5 milliampere multiplied by 1K is a large, approximately is a large drop of 5 volts. So 5 minus 5, essentially output is getting 0, right? What if I increase this voltage to, let's say, minus 1? It will increase my input base emitter junction voltage, VBE, making it more forward bias, making IB increase, making IC increase, and say subsequently the output will again go down. So let us try that. Remember, it is now minus 0.27. So what if we increase our voltage to, let's say, 1 volt, maybe here? Before that, we need to close it. So let's say we do it like 1 volt, close it, simulate it. Now it is like more negative. So you have like minus 1 volt here, and that's how it is getting there. Okay, so this is not going to work. Instead, what we need to do is reduce the value of the resistor RC. That is one better way, or increase the power supply voltage, right? So let's use it like let's say we use the value of resistor instead of 1K, we use like 100 ohm. Okay, and we go back to our original value of negative 0.7 just to forward bias the diode, and we'll see now how things show up. That's very good. Now you see you have like 4.4 volt at the output, making this node coming to be positive as expected, and this junction is reverse bias. This junction is forward bias. So you got this condition satisfied and your transistor is biased in active region. But now, if your DC operating point for the V output starts from 4.4 volt and your supply, maximum supply is 5 volt, so you have only 600 millivolt up, but the down you can go to zero right over here. So therefore, if you want the amplifier to behave as a mid volt, let's say this is your 5 volt and this is your like 0 volt. So you want to start from 2.5 volt. So you need to set the DC bias point accordingly. So in order to do so, you can but then you need to also understand your current requirement. Now here is supplying the 5 milliampere. So if you want to design it for 5 milliampere collector current, you can do one thing, you can increase bit a value of resistance. So here if you want 2.5 volt, so you can apply V plus minus 2.5 divided by IC is 5 milliampere. That will give you the value of RC. So it is V plus is 5 volts. So it is 5 minus 2.5 is 2.5 divided by 5 milliampere. So it is like 500 ohm. Yeah, yeah. Just set like that. We'll do that. So what about we just click here and we'll say this is like 500 ohm. Click OK, simulate. That's correct. So it is almost 2.2 now. You see 2.29. So that's perfectly biased now. Now this is how you got this analysis done. See the current. Collector current is 500, 540 micron or just 5 milliamp. Your 26 microamp is the base current. You have a gain about 200, which is matching with the manufacturer spice model for this transistor. We have seen that in earlier models so many times, so refer to that. That's good. Now before that, before going forward and performing some other analysis such as time domain and uh, frequency response with the AC analysis, let me take you to the let me take you to the little bit theory that we covered in our previous module. Okay, so right, so here if you see, let me get rid of the drawing. In the previous model we got this theory about this circuit which is common base amplifier, and we said we are going to apply the input at the emitter and the base is grounded, collector is the pin where we are taking the output. The small signal model of it can be drawn like this, where The input signal can be modeled with the Thevenin's equivalent, where Vs is the Thevenin's voltage source and Rs is the Thevenin's equivalent resistance. Because you apply input to the emitter, actually you are also sourcing the current into the emitter modeled by this I1. All right, so this can also be modeled as the Thevenin's dual is your Norton's model, right? Where you have a current source and in parallel with that you have a resistance, right? So you call it a RIN and RN. So this is your Norton's network or Norton's current source, which is a dual of your Thevenin's equivalent. Now you have this base, you have this collector, and then here is your emitter. And we've seen that how this model works here. RC is connected to ground from the collector. Because for AC analysis, you short circuit the voltage sources and open circuit the current sources. I'm talking about the DC sources. If you have a load resistance externally connected to the circuit, that is also shown right here. And then there's the output current that flows through this circuit, flows through the load, which is actually IO right here. And if you look at the open circuit voltage gain without RL is infinite. In that case, we got the expression that it is equal to GM times RC. So essentially your RC is setting the gain here for the circuit, which is same as common emitter mode. In the common emitter also, we see the gain was minus GM times RC. Here is there is no minus sign. It means it is non-inverting amplifier. Remember, common base is a non-inverting amplifier, where in a common emitter, it was an inverting amplifier. Provided some conditions like RO. RO was this impedance across collector and emitter. Usually is very, very high. Now you have another expression for a short circuit current gain. You just short this resistor RL and we say that the current output current is equal to the input current, and input current is coming from this voltage source. As I just explained, even though you apply a voltage source with a series resistance, this dual of Norton's network. It acts as a Norton's current source where IN and across is its resistance, right? So your I in what you shown here is your input current and IO is the output current, and gain of it is 1, provided transistor beta is much greater than 1. And then we said that, okay, input impedance of this common base is 1 over GM and output impedance and all that. So we've seen that, right? Now, we go back to our circuit and we are going to do the time domain analysis for it. So what I'll do, I am in the requirement of running the time domain simulation. For that, I need to change the source from DC to time domain timing the periodic uh, from DC to a signal which is time varying. So I'll do this thing. I'll right click this and I see there is this DC value. Do I need to keep this DC voltage here? If I click advanced, do I need to keep this DC voltage? Because now I'm going to choose the sinusoidal, for example. So DC voltage is still there. Yes, I need that because otherwise I need to use some resistors, external resistors to provide the biasing to the transistor to make the transistor operate in an active region. I haven't used the biasing network here. So I need to just for the analysis to bias it, I need to keep it. So DC offset can also be used for that, because from the DC offset it will then DC offset will also work like that. So I don't use that. So amplitude, let's say I'm using 10 millivolt signal. Frequency of it is like 10 kilohertz. Then I don't use other things like 10 cycles I want. So here I am with this sinusoidal source, and now I have perfectly biased this transistor with the DC operating point. Now I will re-enable this transient analysis. For example, I'll just click here and I will just remove that sign and keep the dot. Here it is done. Now I will hit. I want to check the input. So here is my sine wave, which is perfectly showing up with respect to this one. And now you see from the zero, it is varying 10 volt millivolt peak to peak is 20 millivolt. On the other hand, I will right click and add trace. I want to plot output. So here is my output. This is the expression I'm plotting. I can't see them on the same pan, so I will just hit right click, add platform, and then V in up and V down. Output voltage is not shown here. Why? Let me just right click maybe. Zoom to fit. Okay. Is there an issue that we are not getting the output? Okay. That's probably because we missed to put the DC bias here. Minus 0.7, for example. We'll check that in a moment, and now it is done. That's correct. So you basically when you uh, use the sinusoidal, the DC offset voltage is going to provide the DC bias. So here your DC value disappeared actually. So make sure you use that. So you see now you have positive half cycle, output is also positive half cycle, and the gain is about well, let me just zoom in, or maybe just put it in the same. It's not possible to see that. How much is the, remember the gain we just said is voltage gain is GM times RC. So we don't know the value of GM. So for that, we need to use the uh, value of GM. Let me check with that. Value of GM is given here. This GM is basically, we need to refer to our earlier theory. So anyways, we are just seeing our analysis. We are just performing. So GM times RC is the gain setup. So how much is the output? Like you have 3 volt. No, not really. Yeah, or let's say 3 volt. And the swing is 500 millivolt actually. The output is from 2 point, that's starting from 2.3 to 3. So 700. So it's about gain about 70, because you have a 10 volt millivolt peak and 700 millivolt is the output. So you gain about 70, right? So we'll see that. So that's it. So you got this voltage amplification common base working as a voltage amplifier. How about current amplifier? So let's say add plot pane here. Let's say add trace. I want to see the output current. Now where is the output current? I short circuit output current. This is an open circuit voltage gain. So RL is not there. So it's basically I of IC divided by I in I of V1, right? So that's the current gain. And here, just a second, we'll see what the current gain, short circuit current gain is. Like RL has to be 0. Okay, so here you see the output current is your I times RC. Let me just get rid of this. The output current is the current flowing through the load, and the load is RC, and that is the current that flows through your RC, which is basically IRC. Okay, and that's the current that you take from here to deliver to the load. So that current is in the pink here. That is about your how much it is 8 milliampere reaching peak to the positive. And then input current here is right here is also being plot, that is reaching 8 milliampere to the positive. So if you take this output and input on the same plane, you see they are having the same magnitude, both positive and negative. That's why we say the current gain of this circuit is 1. So that's perfectly your IV1 and IRC. You can also plot and print the ratio of it. That's it. So you got this voltage acting as a current buffer, and we've seen that it provides it doesn't really provide any gain for the current. So because its output current is equal to input current, right? But the advantage is that it has a very low input impedance, uh, as we've seen in the previous module, and the output impedance is also a finite value, right? The impedance of this circuit is very low, and impedance is basically the voltage divided by the current, so that is VT divided by IE. So VT is your thermal voltage. Let's say it is 25 millivolt at the room temperature, and the IE is, we see that 5 milliampere for this circuit, approximately 5 milliampere. So it's about just 5 ohm, right? So this is for the common base circuit. For the common emitter circuit, we've seen that our in is VT over IB. So IB is in micron range, VT is 25 millivolts, so it is in the range of kilo ohms. So it's 2 to 3 orders higher than the, even 4 orders higher than the common base circuit. Having said that, we are all set for moving to our next analysis, which is an AC analysis. So let us do that. So what we are going to do, we have this circuit right here. We will just replace the source with the small AC source. We'll click none and put the small AC magnitude of 1 there. And the DC value has to be there of 0 minus 0.7. Otherwise, your circuit will not work. So keep it like this. Uh, we are done with that. And now we will run the AC analysis. Here it's clear. So we'll just enable this analysis by putting dot. Click OK. And now Spice will ask me which analysis you want to run. After I click run, so I will choose this. It has run this analysis. I am on the schematic plotting the output, which is going to help me understand the behavior of this circuit. So as you can see, I have this gain about 39 to 40 dB. That is the gain I am getting here for this circuit, right? How about yeah, so that's my output voltage here, right? And 3 dB point is about 20 megahertz. So I have a good bandwidth also for all the signal frequencies. What if I want to plot and look at the phase? Phase is zero for the band of frequencies of interest. So as I said, it's an inverting non-inverting amplifier, unlike common emitter, which is an inverting amplifier. What about I right click the pane, add plot pane, right click, add trace, and I want to plot the uh, current gain now. So V of VO in the green is divided by AC input of 1 volt as I put up in the source. Now I will just take output current, which is I of RC, for example, and then divided by the input current, which is this one. Look. So as you can see here, what I can see, I have a gain of about, yeah, approximately zero, minus 40 milli dB is like that. So is the output current. How about I just do one thing like delete this maybe and click add trace. IC of collector current divided by the input current I of V1. I have to use the division. Let's do that. Yeah, so it's almost is one and the same thing, and the output is 0 minus 90 or milli dB. So it's approximately 0. If I right click here, then I will use linear. So I get the gain of 1. You see, here also I right click for the voltage. I click linear. I get 96 volt here. That is, so it's like 96 times higher. My output is 96 times higher than the input. So gain of 96 actually. And for the voltage, and for the current gain is 1. So that's all. We've covered this common base amplifier in a comprehensive way. We've got the theory, analysis and design, and we've simulated the circuit. So hope you like this video. If you did so, click the like button, share, comment, subscribe to the channel, and stay tuned for a wider reach. Till then, wish you happy learning.